Last section, 1.5, day 1. Monday is another heavy duty lesson, day 2. And then we have 2 days of review that we don't really need 2 full days for. And then the test is on Thursday, okay? So this is our last section. The test will be 1.1 through 1.5, okay? And so everyone got their notes out, everybody's phones are up, no earbuds in, all that stuff, right? Okay, so so what we're going to be talking about today is imaginary numbers. So I'm going to underline a line here. A radicand, when the value of the radicand is negative, the root is said to be an imaginary number. So I'll break that down for you. So we all know the square root of 4 is 2, right? No one's going to debate that with me. The square root of 4 is 2. The square root of negative 4 is 2i. If you have a negative under the radical, you're going to have an imaginary number as your solution, okay? What the square root of negative 4 is not, is it's not negative 2. I still see that at this level. People thinking that when you have a negative under the radical, your answer is negative. That is not true. A negative under your radical is imaginary, okay? So another concept I want to talk, this word, radicand, it says in here, radicand is the number under the radical, okay? So just another like vocab words, radicand is like the negative 9. Radicand would be negative 4 or 4, okay? So as you guys know, let me show you another example. If I asked you, what's the square root of 16, you would say 4, right? If I said, what's the square root of negative 16, we just learned, or we learned it in Algebra 2, but hopefully we remember. If not, we just went over it. It's 4i, right? You just answer the question. We're not solving an equation. We're simplifying something, okay? But this is really important. This is a lot about what this whole assignment is about, this whole day is about, is if you are solving an equation. So let's say I give you that, and I say solve that. To solve an equation in this form, you would do the square root of both sides, right? What you do to one side, you must do to the other. And you get x here. The square root of x squared is x. And we know the square root of negative 16 is 4i, right? But don't forget, what am I about to say? What do we have to always remember when we take the square root of something? Plus or minus. Yeah, good. 4i. We should get 2 solutions when we take the square root. Why is that different from that? It's all about how it's presented to you. If I just say, what's negative, the square root of negative 16, it's just 4i, not plus or minus 4i. But if you are solving an equation, in other words, you are taking the square root of both sides, that step right here of doing that square root is called taking the square root. If you are taking the square root of both sides, in other words, it's in an equation, that's when you have to remember to put the plus or minus, okay? So you'll see that coming up, and I just want to talk about that going forward. So complex number is just putting a real part of an equation and an imaginary part together. So you might have an answer of 4 plus 5i, okay? That's a complex number. So you have real and imaginary mixed together. And this little box here is just telling us when we have real and imaginary numbers together, we put it in that form. Just like we have standard form, exponents in descending order, slope-intercept form, y equals mx plus b. This is just the order we put them in, okay? Now, there's something called the fundamental theorem of algebra. There's a lot of big words in there, blah, blah, blah. I'm going to narrow it down for you of what you need to know, so don't worry about all of that. But what you need to know, we're just going to squeeze it in over here. Really important, another big concept today. The degree, and we'll break this down in a minute. Let's just write it. The degree of a polynomial equals the number, not hashtag, the number of factors and or solutions. So let me give you a second to write that, and then I will explain it. Degree of a polynomial equals the number of factors and or solutions. Degree. We talked about degree a couple of days ago. Degree is the biggest exponent, right? The exponent that has the largest value. That number tells us lots and lots about a polynomial. Here's another thing that we've learned, and that is that equals the number of solutions. Look at that example I already did up here. This is a degree 2 equation. This is degree 2. The biggest exponent is 2. We should have 2 solutions, and we do, a plus 4i and a minus 4i, or positive and a negative 4i, okay? So that's really important. The other thing is that word root got thrown in up at the top. Root is 0. Same word. So now we can add to our really long list of what we call x-intercepts. So x-intercepts are zeros, x values, solutions, and now you might hear root. So don't let it throw you off. It's just another word that means the same thing. Okay? All right. So this first example we're going to do is we're going to factor this. We're going to factor. Okay, I told you factoring never goes away in this class. We're going to factor a lot today. Luckily, I'm doing it all with you, so hopefully it's a little bit of a review for you, but I'm not going to go super slow because really we need to know how to factor at this stage of the game. And so if you remember, the first step of all factoring is GCF, right? So we can factor an x right out of there. And then half the battle is knowing, am I done or not? And so you look at the set of parentheses, and you say, oh, that looks like one of the chart problems. My teacher calls it a chart problem. She makes that little chart off to the side. Okay, let's do that. And remember, you're multiplying and adding here. 1 times 13 is 13, and negative 6 is our b value. So what is that? What two numbers multiply to get 13 and add to get negative 6? Say it again. It's not possible. You're right. It's a trick question, kind of. I'm not trying to trick you, but so if this had been any math moment in your life up until this minute, you would have said, I'm done. I can't go any further, including on our quiz. But now that I've introduced complex numbers, meaning real and imaginary, we are going to be able to factor this. So we've been telling you lies all along. I'm going to tell you another lie. I'm going to tell you about another lie I gave you in a minute, too. But so here's the thing. This is not factorable the traditional way, the way that we've learned how to factor. But we're going to find a workaround by using the quadratic formula. I'm going to solve this using quadratic formula and then put my solutions in factored form, which is very, very simple, okay? So anytime a polynomial is not factorable in one of our little methods, it means it's got imaginary numbers as its solution. You're going to get i's or radicals in your solution. So let me just stop there and write quadratic formula. So I know you guys have all seen this before. I know some of you have it memorized still, and I know some of you don't. The very first test, I will be nice and give you quadratic formula on the test, because there is a question on the test where you have to use it, okay? But really, we should know it, especially by the time we're done with our first test, okay? How many of you kind of do remember it? Yeah, there's songs and everything, right? All right, so if you know it, great. If you don't, I will give it to you. But once you have it, we should have no problem plugging in and simplifying, okay? So I'm just identifying A, B, and C. So A is 1, B is negative 6, and C is 13. So I'm going to take a second and plug all those numbers into quadratic formula. So remember, when you plug a negative in where there's already a negative, it changes it to positive. If you're doing a negative number to a power, it must go in parentheses. Okay. Stop me if you have a question of where I put something or why or any of that. Okay, now we go into the radical. If you type in your calculator negative 6 squared without parentheses, you're going to get the wrong answer. I wouldn't even bother putting it in your calculator. It's just 6 times 6. You know 2 negatives make a positive. 6 times 6 is 36. I'm just going to use the space right above my radical. And then I'm using my notes. I put in my calculator, negative 4 times 1 times 13. I already put it in my calculator, and I got negative 52. So that black part of my problem is really under the radical. Okay, I'm just using that as workspace up there. So I have 6 plus or minus. When I do 36 minus 52, I get negative 16. So I put it back under there. Okay. Yes, we are solving an equation here, and we have a negative 16 under the radical. But what's nice is quadratic formula has the plus and the minus. Remember, we had to remember to put it here when you took the square root. In this one, it's built in, so you're going to get your two solutions naturally. And negative 16 is 4i. So I have 6 plus or minus 4i over 2. And we can simplify that one more way, and that is dividing my numerators both by 2. Okay, so I get 3 plus or minus 2i. Guys, that's two solutions. X equals 3 plus 2i, 3 minus 2i. Okay, so that's two solutions for the quadratic. But what we had to do is write it in factored form. So when I write this in factored form, don't forget about that x that we factored out at the beginning. And then we're going to have two parentheses, make them kind of big, okay? This is going to be my solution in a minute, okay? Just getting ready for it. How do I get this solution in factored form? It's really simple, okay? So let me write it out as two separate ones. And you don't have to show this work, okay? It's pretty simple. I'm just writing as 3 plus 2i, 3 minus 2i, right? Those are two solutions. It looks funny, but that's what it is, okay? How do I write these in factored form? Well, let me go off on a little baby tangent. Don't write this. I just want to show you guys something. So look, if I factored something, some polynomial, and I got this. Those are the factors, okay? These are factors. What if I said solve it? Solve them. What would you do? Set them equal to 0 and solve. Would you show the work? It's up to you. I wouldn't require it. I'm just being obnoxious, showing every step so I don't miss anybody that might be questioning it. So you get x equals negative 4, x equals 7. Those are your zeros, roots, solutions, whatever, okay? Factored form to zeros. Let's work in reverse. What if I said, here's some solutions, write them in factored form? What would we do to work backwards? You would just undo what you just did. Bring the 4 back to the other side. Now in factored form. Bring the 7 to the other side. So you can go from factors to zeros or zeros to factors. You're just moving. Guys, remember, if you just move things from one side of an equation to another, you're allowed to do that. To go from factors to zeros, we're moving everything to the right side, or, to the other side, getting the x by itself. Let me say that. And if we're going from zeros to factors, we bring everybody back to one side together. Okay? Does that make sense, that concept? So do the same thing here. Bring the 3 over and the 2i over. You would have x minus 3 minus 2i. Same thing here, x minus 3 plus 2i. And that is your factored form. Solutions we got from quadratic formula. Move everybody to the other side of the equation. There's our 3 factors for a cubic. Remember, your degree tells you how many solutions or factors you have. This is degree 3. We should have 1, 2, 3. X is a factor. If you have an X in you, you are a factor. Okay? So we'll practice that more. Next page. Another lie you've been told in your life. So same directions, different type of problem. Factor. We're going to factor this. okay? So let me remind you of something that is on your factoring quiz. If I asked you to factor this, you'd say, oh yeah, that's the difference of two squares. I remember that. I hope you would say all this stuff to yourself. 2 parentheses, 2 different signs, right? Square root of 100x squared is 10x, right? Square root of 100 is 10, square root of x squared is x, and the square root of 9 is 3. Done. Factor. We love those. They're easy. What if I gave you this, though? If this were on your current quiz that you're retaking, you'd say, there's nothing I can do. There's no GCF. It's not the difference of 2 squares. It's the sum of 2 squares. But when we're talking about complex numbers, you actually can write this. You can factor it. It's super easy if you just know this. Watch. You go, oh yeah, I can do this if I use imaginary numbers. Same idea. 2 parentheses, 2 different signs, and I'm going to do the square root of the front and the square root of the back. Watch the only difference. So I'm going to have the 10x and the 3. It's just the second number is going to have an I on it. That's it. It's the only difference between difference of 2 squares, sum of 2 squares. If you want to know why this is, you could solve this using quadratic formula like we did on the last problem, and you would see that this is the 2 answers you get, okay? It's for the same reasons that we just did on the other paper, on the previous example. I'm not going to go through and do quadratic formula again. It takes too much time. But A is 100, B is 0, because there is no middle term, and C is 9. So if you wanted to prove it to yourself later, by all means, do quadratic formula. You'll see you get this answer. But with this problem, it's really similar to the way we factor this problem, so we don't have to do quadratic formula. It's shorter, okay? So let's take that same concept and look at this problem. Always the first step with factoring is GCF. So I'm going to factor out a y. Right? They have a y in common. And again, if this was your quiz, you'd be like, there's nothing else I can do. If that were a minus, I'd know I get 2x plus 5, 2x minus 5. But we just learned that you can factor a sum of 2 squares using imaginary numbers. So 2 parentheses, 2 different signs. Square root of 4x squared would be 2x. Square root of 25 is 5. And because it was a sum, we just throw an I in there. Done. Factored. Now that I told you that all of your math teachers have been lying to you, including me, all these years, because now you can factor anything, we only do this stuff in this section. After we get past 1.5, we don't really deal with imaginary numbers the rest of the year. We're kind of touching on imaginary numbers. They exist. This is how we deal with them. And then, done. You won't see them very often, okay? When you get the test review next week, as I keep promising you, you will see what you're expected to know on the test. Don't stress, okay? Really, please don't stress about that. All right. Continuing with the theme of I'm not real happy with these notes is our second to last example, which is right here. Even an odd multiplicity. This is super important, super easy, okay, promise. But there's no homework problem. She didn't put any of these in the homework to practice. So I haven't had a chance to look forward to other sections, and I can't remember. I think this comes up later on again, and so we'll touch on it again. But I'm going to touch on it here because it fits in with what we're talking about, so it's kind of important. But it's really, really simple. Don't be scared. So here's the thing, and we all teach this in Algebra 2, so this might sound familiar, okay? If a polynomial function has a factor that is repeated, those duplicate roots, solutions, whatever, are labeled as multiplicity. Really simple concept. Let me give you an example. If I said x plus 2 and x plus 2 were 2 factors, that means we have 2 of the same factors or same zeros, right? If I set them equal to 0 and solve, I get -2. So that's a multiplicity of 2. If there's 3 of the same thing, that's a multiplicity of 3. If there's 10 of the same thing, it's a multiplicity of 10. That's all that means, okay? That's what the word multiplicity means. How many of the same exact thing do we have, okay? Now, multiplicity tells us how a graph interacts with the x-axis. If you have an odd number, your graph will cross at that 0. So x is your, whatever the x value is, always y is 0 on the x-axis. And I'm going to show, we're just writing the notes right here. I'll explain this really well with a picture, don't worry. If you have even multiplicity, 2, 4, 6, 8, then your graph will touch and turn, also known as bounce, okay, at that x-intercept. Now I'm going to show you that in a picture. So example 3 is factored for us. Look, they give us a factored polynomial, and it's been graphed on a graphing calculator for us. Okay, so it's factored and it's graphed. Let's look at the graph for a second. We have 2 x-intercepts, one here, one here, right? Those are our zeros. Those are our roots, our x values, our solutions. This one is at 1. This one is at -2. Okay? We'll come back to that. Let's look at what we have here. We have x plus 2 3 times. So instead of writing x plus 2 1, 2, 3 times, it's a shortcut way of writing it, right? That means that, okay? It's just 3 of the same thing. Let's find the zeros, which means you set equal to 0 and solve. Same thing with x minus 1. There's 2 of them, but instead of writing x minus 1 twice, we write x minus 1 to the second power, means 2 of those. We can find its 0. And do you need to show this work for me? Absolutely not. I'm just making a point here. These are our zeros. We know our graph is going to touch the x-axis at -2, there it is, and at 1. But we can go a step further with multiplicity. How many -2's do we have? 3. So we would call that a multiplicity of 3. That means we're going to cross at the x-axis. And that's what it does. So, because 3 is an odd number. Odd. Odd multiplicity crosses. 3 is an odd number. Not what the x value is. That's not what we're talking about. The multiplicity is odd. It crosses. And you can see it goes right through the x-axis. Cross. That is a cross. Okay? How many 1s do we have? 2. That's a multiplicity of 2. 2 is an even number. So we bounce or touch and turn. So if you look, I like to use bounce because it's less letters, fewer letters. We touch and turn. We bounce. Like a ball, you hit the ground and you bounce up. So you bounce. So anytime you have even multiplicity, you are going to bounce. Whether this is a multiplicity of 2 or 200, okay, you bounce. If you have an odd multiplicity, 1, 3, 301, you're going to cross, okay? So just look at this example here. We're not going to do it all, but there are 3 x-intercepts, right? 1, 2, 3. Because this x value crosses, we know, no matter what, that our multiplicity will be odd. We'll either have 1, 3, 5, 53, some odd number of multiplicity. This one bounces, so it would have even multiplicity. And we have another one that is odd. We know it's odd, again, because it crosses. Okay? So here's where multiplicity tells us how a graph interacts with the x-axis. Now that I went over that, file it away somewhere. We'll talk about it again another day because it's not in today's homework. Say it again. Because it crosses, right? It goes right through it, just like this one goes through it. That's a cross. Crosses over from one side of the x-axis to another. Anytime your multiplicity is odd, we cross. So we don't know what it is, by the way. We don't know if it's 1, 5, 57. We just know it's odd, okay? All right, last thing. Conjugate root theorem. And then we're going to do our homework together. We're almost there, I promise. And this is easy. Easy, easy. Conjugate root theorem. Again, terminology you don't have to memorize, okay? You don't have to memorize that is what this is, okay? But what we need to remember is this. Anytime you take the square root of something, you're going to get two solutions. Anytime a radical is involved in an equation, you have two solutions. You have a plus or a minus, okay? You don't have to write this again if you don't want to. I'm just making a point. If I solve this, I would get x equals plus or minus 2i. If I solved this, square root, I would get x equals plus or minus, square root of 7. I don't know what that is. It would be a decimal. I can just leave it under the radical. So anytime you do the square root of something, you get a positive and a negative answer, okay? So what the conjugate root theorem says is that if you have a solution of a plus the square root of I, don't write that. You would have a solution of a minus the square root of b. Sorry, I said I. Yeah. A plus the square root of b, a minus the square root of b. Why? Because if you are a radical, you travel in pairs. There's two of you, a plus and a minus, for the reason I just showed you right here. Okay? Same thing with i's. I's, think about this, i's travel in pairs. Because where did the I originate from? Under a radical, right? Before he was an I, he was a number under the radical. So i's and radicals travel in pairs. Let me explain why this is important. Ignore the corollary. Last example. A polynomial function has a degree of 5. Why is that important? Well, we know we're going to have 5 answers or 5 factors. They're giving us 3 of them. They're giving us x equals 2, x equals 3i, and x equals 1 plus I. Those are given to us. They're asking, what are the remaining zeros? Well, how do we do this if we don't have the polynomial? Like, where's my factoring? Where is my quadratic formula? Whatever. We don't need it because of the conjugate root theorem. If you are an I or a radical, you have a conjugate, a friend. You travel together. You always have a positive and a negative. So if we have these 3, how many are we missing? How many total should there be? 5. So we're missing 2, right? That's important. Remember, the degree tells you how many solutions you have. They gave us 3. We have to figure out what the other 2 are. Does the number 2 have a conjugate? No. Does 3i have a conjugate? Yeah. Yep, it's 3i. Negative 3i. Sorry. Does 1 plus I have a conjugate? Yeah. 1 minus I. If you are an I, you have a friend that you travel with. Okay? There's always a plus and a minus of every I and every radical. That's it. Okay? Just knowing that. Okay? Okay. Let's go to practice set 1. We're actually going to do 1 through 3. Change that to a 3. And I'm going to do all of them with you right now. It's a short assignment, but, there's a little bit of work in here. We have a degree 3. They gave us x equals 3, x equals 2i. Those were given to us. How many are we missing? 1. Degree 3 means 3 solutions. And so if we have positive 2i, we also have a negative 2i. Okay? That's what we just did in our last example. But I want you guys to, we're going to take it a step further. It says to write the linear factorization of the polynomial. Guys, all that means is write in factored form. Because I feel like we need practice in this. So you're going to call your function f of x, g of x, j of x, z of x, I don't care. And then put your solutions in factored form. Remember? Bring everybody to the other side. So x equals 3 would become x minus 3, right? Just subtract it. X equals 2i would become x minus 2i. And x equals negative 2i would become x what? Plus. Yeah. You don't have to show the work. You guys know if it's minus on one side, it becomes plus on the other. If it's a positive on one side, it becomes negative or minus on the other side. Okay? And that's it. Degree 4, they give us 2 zeros. So we're missing 2. I has a conjugate. It's called negative I. I's travel in pairs. If you have one I, you have to have 2. If they give you one, you know there's another one. There's always going to be 2 I's. And if you have a radical, you're always going to have 2 of them. If they give us the positive one, we know that there's also a negative. I's and radicals all have conjugates. So there's our 4 zero solutions roots. Let's put this in factored form. Pick your letter, I don't care. And just bring those numbers, letters, whatever.
Good afternoon, Countryside High School teachers and students. Pardon this interruption. Teachers, if you have not played the Cougar TV announcements, please do so. We're going to transition our morning announcements to make sure everyone's watching the third period Cougar TV announcements, which Coach Patterson's group produces each and every day. Happy birthday also to Janine Gauvin. Janine, we hope you have a great day. And Cougars, thank you for doing a great job with your electronic devices. General reminder, no headphones in the concourse unless it's lunchtime. Thank you.
Okay, are we good on number 2? All I did was bring each of those to the other side. Are we getting that? The order doesn't matter, by the way. Okay, the order of these factors can be in any order you want. All right. Last one, we can skip number 4 unless you want to do it on your own. I'll put the key on canvas. Degree 4, they gave us 2 of them. They both have I's and radicals and stuff, so we know they have a conjugate, so we'll write those. So negative 3i would have positive 3i, right? Those are conjugates. And then this guy would have 1 minus I square root of 3. These two are conjugates. You see it? Good. Put it in factored form. X plus 3i, that's this one. You're just moving 2 things to the other side. They're both positive on the right side. When they'll both come to the other side, they'll both be negative. Okay, you just change the sign. So that'd be x minus 1 minus I square roots of 3. That's this one. X minus 3i, that's this one. And then x minus 1, that's moving the 1 over, and then plus I square roots of 3. You okay on 1 through 3? Yeah? All right, let's do some factoring. Your favorite together. Number 13. It's a good review, too. Both of these. 13 is a polynomial with 4 terms. The method, let me read the directions. Find, solve. find the zeros. Okay, so solve it. So we're going to start by factoring. Whenever you have 4, we do our 2 and 2. Factor out a 2x, factor out an x squared. That's x squared. Factor out a negative 7. If you did it right, your parentheses should be the same. And then you write your factored answer. Okay, but we're solving. So if we're in factored form, really easy to solve. We just set them equal to 0. And this is a place where I wouldn't care if you showed a lot of work. Okay. I would add 7 and then take the square root. Don't forget, when you take the square root, you put a plus or minus. This is a degree 2. This part of the problem, we should get 2 solutions, plus or minus, square root of 7. That's plus or minus the square root of 7. Right, square root of both sides. And then we get also negative 2. Total of 1, 2, 3 solutions. Degree 3 should have 3 solutions. So, you write it later. 1, 2, 3. So whenever you have 4 terms, parentheses, parentheses, set them equal to 0, solve. You might have radicals in your answer. You might have i's in your answer. You might have plain old boring numbers like negative 2 in your answer. Okay? We haven't seen this type of factoring in this class so far, except you have. Weird. It looks like your chart problem, except it has a 4 here instead of a 2, and a 2 here instead of a 1. We factor it almost identical to doing a chart problem. There's only one difference, and I'll show you in a second. So asking ourselves, what 2 numbers multiply to get 8, add to get 6? This one is factorable. What are the numbers? 4 and 2. 4 times 2 is 8. 4 plus 2 is 6. Since this has a 1 in front, we get to do the shortcut method. We don't have to do like the bring down the outside 2, split the middle. So we're going to get 2 parentheses. The only difference with this being a 4 here is what we put here instead of x is x squared. That's the only difference. It's an x squared instead of an x. And then it doesn't matter if you bring the 4 or the 2 over first. Set them equal to 0 and solve. In the end, we should have 4 solutions, right? It's a degree 4. We should have 4 solutions. I would subtract 4 here, so I have a negative 4 on that side. Square root, I get x equals, tell me, plus or minus, not square root of 2. That's okay. What is this one going to be? 2i. Yep, plus or minus 2i's. That's okay. You were doing that one, yeah. So always a plus or minus if you take the square root. The negative makes it an I, and the square root of 4 is 2. Okay? Subtract 2. Square root, x equals, we're going to have a plus or a minus. Can't leave a negative, we never leave a negative under the radical. Even if you can't take the 2 out, that's okay. We bring the negative out, it becomes an I, and the 2 is just left underneath the radical. That's a total of 4 solutions there. 1, 2, 3, 4. Degree 4 should have 4 solutions. That was a lot, right? We are done.